value of 7,777 squared divided by 5,555 times 2,222. To do this question, we start off by noticing that all these numbers have a factor of 1,111. So we start by removing that factor of 1,111 from each of the numbers. Then, by using this exponent law, we simplify the numerator to 7 squared times 1,111 squared. On the denominator, we do 5 times 2 to get 10 and then merge the 1,111s. Now, we notice that the 1,111 square terms cancel each other out, giving our final answer of 49 over 10, or the C. Question 2. Jessica rolls 5 dice. She rolls 19 points in total. What is the maximum number of 6s she could have rolled? We proceed by guess and check, starting with option E, 4. If she had rolled 4 6s, if we minimize the last dice, she must have at least gotten 25 points. Since 25 points is greater than 19 points, this is not possible. Then we go to question D, 3. If she got 3 6s and the other 2 dice are minimized to be 1s, she must have at least gotten 20 points. Since 20 points is greater than 19 points, this is also impossible. Now we go to C, 2. 2 6s. If we get 2 6s and then have minimized the other 3 dice, she must have at least gotten 15 points, which is less than 19. So this could be possible. If we add 4 more points to the third dice, since 4 more points to 15 is 19, we get a possible dice roll that gives 19 points and have 2 6s. So 2 6s is possible. Since 2 6s is the maximum number of dice 6s possible, the answer is C, 2. Question 3. A cylindrical can has a height of 15 centimeters and the perimeter of its circular base is 30 centimeters. An ant walks from point A on the base to point B on the top. Point B is directly above point A. The ant's path is either vertically upwards or horizontally along the circular arcs around the can. A path is shown with a thicker line, black for the path on the front of the can and gray at the back. What is the length in centimeters of the ant's path? To do this, we split the ant's path into 2 parts. The ones where it goes directly upwards, which I'll show in red, and the ones that go directly horizontal, forming circular arcs, I'll show in green. Now we're gonna start by finding the length of all the green paths. If we add all these green paths up, we notice we go around the circular base twice. We know that the circular base is 30 centimeters. So since we go around circularly twice, the total distance circularly is 2 times 30 centimeters, or 60 centimeters. Now we consider the red paths. If we add all the red paths together, we get a vertical line going from A to B. If we also know that the cylinder can has a height of 15 centimeters. This means that the length of all of the red lines combined is 15 centimeters, since that's the height of the can. Now we add these 2 together to get the total length of the path of the ant, which is 15 plus 60 centimeters, or our answer of 75 centimeters. Question 4. Maya has 4 differently colored pens. She wants to color the 3 striped rectangular flags shown in the diagram so that each stripe is a single color and no 2 adjacent stripes are the same color. In how many ways can she do this? Well, we start by looking at how many ways can I color this top stripe. This top stripe has 4 different colors, and there are no extra restrictions, so that there are 4 ways to choose this top stripe. Now we look at the next stripe below that. On this stripe, while there are 4 differently colored pens, we know that one of them won't work because then it would be the same as the top stripe. So this one only has 3 possible options. Now we look at the bottom one. The bottom one would have had 4 options, but one of the options you can't do because then it would be the same as the middle flag. So this one also has 3 options. Now we multiply all of these numbers to find the total number of ways she can do this, or 36 ways, which is option D. 5. We call a positive integer n 2 prime if it has exactly 3 different divisors, namely 1, 2, and n itself. How many different 2 prime integers are there? We start by noting that if 2 is a factor, then n divided by 2 must also be a factor. So there are only 2 cases. N divided by 2 is just 1, which makes one of the possible 2 prime factor numbers 2, or n divided by 2 equals 2, which makes another 2 prime number 4. These are the only 2 prime numbers, which means the answer is C, 2. Question 6. How many pairs of positive integers x and y satisfy the equation x plus 2y equals 2 to the power 10? We start off by noting that for every y, there is an x as long as y is less than 2 to the power 9 and y is greater than 0. If y were to equal 2 to the power 9, then x would equal 0, which is not positive, so it is not possible. If y is greater than 0, is equal to 0, then y isn't positive, so it's also not possible. So y must be in the range from 1 to 2 to the power 9 minus 1. A useful trick to know in many questions is that in between a and b, there are b minus a plus 1 numbers, including a and b. Between 1 and 2 to the power 9 minus 1, there are 2 to the power 9 minus 1 plus 1, or 2 to the power 9 minus 1 numbers, which gives us our answer of A. Question 7. 2 equilateral triangles are put together with their opposite sides parallel to form a hexagon. We know that the length of 4 sides of this hexagon is shown in the diagram. What is the perimeter of the hexagon? First, we're going to use our given information to make a new diagram like this. Here, we know that the red is correct because it does say the triangles are equilateral, and we know that equilateral triangles have all 60-degree angles. We know that they are parallel because it also shows given that the opposite sides are parallel in the question. And the hexagon is also blue, is already given in the question. So now, the real question is how do we find the perimeter? But first, let's use these parallel information. We know that this 60-degree angle is equal to this angle because of the parallel lines. Since the sum of all angles in a triangle is 180, we also know that this is 60 degrees. Since all angles in this triangle are 60 degrees, this is equilateral. And we can do this for all the other triangles on the outer edge to show that they are also equilateral. Now I will write a few lengths. We're going to let this side be x, and we're going to let this side be y. Now we're going to use this information. Since this is equilateral, this side is 12, this side is 12. Since this triangle is equilateral, this side is 11, this side is 11. Since this triangle is equilateral, this side is 15, this side is also 15. Since this triangle is equilateral, this side is y, and this side is y. Now we know that this big triangle shall show in yellow. This entire we're going to use these two sides. These two sides are equal because they're the two sides of an equilateral triangle. Because from given information, we know that the two bigger equilateral triangles are also have the same length. So, using this information, we know that x plus y plus 12 equals 12 plus 11 plus 15. These are just adding the two sides of the triangle, which gives us that x plus y total up to 26. Now we look at solve the perimeter of the hexagon, which gives us x plus y plus 6 plus 15 plus 11 plus 12. We're just using all the side lengths that were given, but which becomes x plus y plus 44. But we don't know x and y individually. But we do know that x plus y is 26. So we use that information to get 26 plus 44, which equals 70, which gives us the answer of D. Question 8. A square with area 84 is divided into 4 squares. The upper left square is colored black. The lower right square is again divided into 4 squares, and so on. The process is repeated an infinite number of times. What is the total area that is colored black? There are 2 methods for this. One that is pretty easy to understand but is a little longer, and the other one is very hard. It's a little harder to understand, but it's like one line. So let's start with the longer but more easier to understand method. We know that this square is 1/4 of the area of 1/4 of 84, or area of 21. This entire square has an area of 21. So this square, which is again 1/4, is 21 over 4. And this process goes on. So the area of all the black squares is this sequence. This sequence is coincidentally a geometric sequence. So we find that A, which is also known as the first term, is 21, and the common ratio, what fraction you multiply each time to get your second number, is 1/4. Then the area can be found using the formula for an infinite geometric sequence, A divided by 1 minus R. Using this formula, we get our answer of 28. Now, let's look at the other method for this. Using the other method, we're going to split it into these parts that I'll show in red. Each of these parts has the black area takes up 1/3 for each of these parts, because there are 2 white squares and 1 black square. So there's 1 black square and 3 squares. So the area is 1/3 of the entire part. For each of these parts, since it's 1/3, the black will also take up 1/3 of the entire figure. So the answer is 1/3 times 84, or 28, which also gives our answer a B. Question 9. Each of the integers from 1 to 9 is to be placed in one of the 9 boxes in the picture, so that any 3 integers placed in consecutive boxes add to a multiple of 3. The numbers 7 and 9 have already been placed. In how many different ways can the remaining boxes be filled? We're going to use some modular arithmetic for this. So first, we take the remainder of 7 and 9 when you divide it by 3, which would be 1 and 0. Now we're going to do some differently. We're going to make sure every the sum of every 3 consecutive integers is 3. We can see that this works because if a number has remainder of 1 and is added by a number that has remainder of 2, it will equal a multiple of 3. So this will be 2. This is also the same as the sum of any 3 consecutive integers being 3. So now we fill this entire thing in. So 2 plus 1 plus 0 is 3, 0 plus 1 plus 2 is 3, 1 plus 2 plus 0 is 3, 2 plus 0 plus 1 is 3, 0 plus 1 plus 2 is 3. Now that we filled this entire thing in, we are gonna now actually fill in the numbers from 1 to 9. So, let's start with the zeros. We have the numbers 3 and 6 to place. Since 9 is already placed, there are 2 ways to place the 3 and 1 way to place the 6. So there's 2 ways for the remainders of 0 to be filled. Now we place the remainders of 1. Again, we have to place 2 numbers, 1 and 4. There is 2 ways to put the 1 and 2 ways to put the 4. So there are again 2 ways for remainder 1. But for remainder 2, this is special. We have 3 numbers, the number 2, the number 5, and the number 8. There are 3 ways to put the number 2, 2 ways to put the next number, and 1 way for the last number, for 3 times 2, or 6 ways for the remainders of 2 to be filled. Multiplying all these up, we get a total of 24 ways, which gives us the answer of E. Question 10. What is the units digit of the product 5 to the power 5 plus 1 times 5 to the power 10 plus 1 times 5 to the 15th plus 1? We start by listing powers of 5 to see any pattern for the last digit. 5 to the power 1 is 5, 5 to the power 2 is 25, 5 to the power 3 is 125. You should probably remember these. 5 to the power 4 is 625, and if you want, 5 to the power 5 equals 3,125. If you look at the last digits of each of these numbers, 5, 5, 5, 5, 5, we can see that all of the last digit of all powers of 5, except 0 and all the negatives, is going to be a 5. So now we're going to use this to our advantage. This means that the last digit of 5 to the power 5, 5 to the power 10, and 5 to the power 15 all are 5. Here's a useful trick for these types of problems. You don't have to use it in this problem, but it's useful for many of the other types of these problems. The last digit of the product is the last digit of the product of the last digits of the multiples. That probably doesn't make sense, but I'll explain with you some examples. For example, here, to find the last digit of 58 times 32, we will take the last digit of these two numbers, 8 and 2, and multiply them to get 16. The last digit of 16, 6, is the last digit of this product. Similarly, for 43 times 29, again, we would take the last digits of these, and we would multiply them to get another number, and then the last digit of that number is the last digit of the product. Now we won't use this here because as we'll see, what last digit of this is the same as the last digit of this. Remember, the last digit of 5 to the power 5 is 5, 5 to the power 10 is 5, 5 to the power 15 is 5, which when you multiply, you get 6 times 6 times 6, which is 216. And the last digit of 216 is 6. And that will be our answer. Question 11. A triangular pyramid has edges of integer length. 4 of these lengths are shown in the diagram. What is the sum of the length of the other 2 edges? We're going to let this edge be x. Now we're going to reference 2 different triangles. This triangle that I'm going to show in red, and this triangle that I will show in blue. call the triangle inequality that if A, B, and C are the sides of a triangle, then A plus B must be greater than C. In other words, the sum of any two sides must be greater than the third side. This is true, or else the triangle would turn into a line or not exist. From the red triangle, we know from the triangle inequality that x must be less than 7 and x must be greater than 1. From the blue triangle, we know that x must be less than 9 and x must be greater than 5. From the conditions x is greater than 5, from the conditions x is greater than 5 and x is less than 7, we know that x must equal 6, since x must be an integer, and the only integer between 5 and 7 is 6. Now we're going to reference two other triangles. So back to this diagram, we are going to set another side length, the other missing length, to y. And we're going to have two other triangles. This triangle, which I'll reference in green, and this triangle, which I'll reference as yellow. Now, from the green triangle, we see that y must be greater than 2 and y must be less than 6. And from the yellow triangle, y must be less than 10 and y must be greater than 4. From the conditions, y must be greater than 4 and y must be less than 6, y must be an integer makes y equals 5. And now we know the two unknown lengths, so the answer is 6 plus 5, or 11. Question 12. For a positive integer n factorial is defined as the product of all integers from 1 to n. For example, 4 factorial equals 4 times 3 times 2 times 1 equals 24. What is the sum of the digits of n if n factorial equals 6 factorial times 7 factorial? We know that 7 factorial equals 1 times 2 times 3 times 4 times 5 times 6 times 7. The 6 factorial should add the next few terms to this, like 8, 9, 10, starting from 8 and going up to n. So we start with 6 factorial. And our goal, we'll start by trying to make the term 8, then we'll try to make 9, then we'll try to make 10, then we'll try to make 11, and so on. So, then we're going to break apart each one. So the 6 will turn into the 2 and the 3. The 4 is going to turn into a 2 and a 2, and that's it. Then, we're going to merge all of them using the exponent rules. So there are 4 2's, so that makes the 2 to the power 4. There are 2 3's, so that makes the 3 to the power 2. And there is 1 5, so that will make the 5. Now we use this term to make 8. So using exponent rules, we can split the 2 to the power 4 to 2 to the power 3 and 2 to the power 1. And 2 to the power 3 is 8. Now we're going to go and make 9. So we take our 3 squared term and make it 9, since 3 times 3 is 9. And now the remaining 2 times 5 make 10. So now back to evaluating 6 factorial times 7 factorial, the 7 factorial part, this 7 factorial part becomes 1 times 2 times 3 times 4 times 5 times 6 times 7. And then the 6 factorial part, as we found out just here, becomes the 8 times 9 times 10. So n factorial is equal to 10, which means n factorial equals 10 factorial, which means n equals 10. So the sum of the digits in n is 1 plus 0 or 1. Question 13. The graphs of the function x cubed plus 3x squared plus ax plus 2a all pass through the same point, no matter what value of a is chosen. What is the sum of the coordinates of that point? Our goal is to find an x value such that the a term cancels each other out, which would satisfy the statement that no matter what value of a is chosen, that the value would stay the y coordinate would stay the same. The only x that works is x equals -2. So then only -2a plus 2a would equal 0. Substituting -2, we start with this. We substitute -2. Then we cancel out the -2a and 2a. Then we evaluate the exponents. Then we add and gives our 8. And now our coordinate is -2, 8. So when we add those, we get 6. And 6 is not one of the answer choices, so the answer is E. Question 14. We are given 5 numbers, A1, A2, A3, A4, A5, whose sum is S. For each k is greater than or equal to 1 and less than or equal to 5, we know that ak equals k plus s. What is the value of s? We start out by using the given information that the 5 numbers a1, a2, a3, a4, a5 is sums up to s. So we make this equation s equals a1 plus a2 plus a3 plus a4 plus a5. Now we use this fact that for each a1 k greater than or equal 1 to less than or equal to 5, we know that ak is equal k plus s. Using this fact, we get this new equation, and we now can easily solve for s. We combine like terms, we subtract 5s on both sides, and we divide by -4 to get our answer of 15/4, or B. Question 15. How many pairs of integers m and n satisfy the inequality absolute value of 2m minus 2023 plus the absolute value of 2n minus m is less than or equal to 1? To do this question, honestly, I don't like big numbers. Like this 2023, that's going to annoy me so much. So I'm going to substitute to remove that 2023. We substitute m equals m plus 1011, so that when the 1011 is distributed, we get 2022, and that cancels out easily. But on the right side, now we have a minus 1111 terms, which is, while it's definitely better than 2023, is still pretty large. So we'll do another substitution, but this time with n. Let n equals capital M plus 505. When we do this, now we will only affect the right absolute value, and then this will cancel out and turn to this much easier expression to deal with. Now we just guess and check. If m is less than or equal to 1, then the absolute value of 2m minus 1 is greater than or equal to 1, which means it won't work. If m equals 0, we check the n values, it also doesn't work. If m equals 1, there is a solution when n equals 0. And when m is greater than or equal to 2, then 2m minus 1 is greater than 1, and hence is also impossible. So there is only one solution, which gives us our final answer of B. Question 16. There are 23 animals sitting in a row at the cinema. Each animal is either a beaver or a kangaroo. Everyone has at least one neighbor who is a kangaroo. What is the largest number of beavers in the row? Think like the kangaroos, giving spots for the beavers to sit in. You want to maximize the number of spots available for the beavers. This means having each beaver next to only one kangaroo, and each kangaroo being next to one beaver. We start with a kangaroo one space to the right of the edge. So I will denote the kangaroos with a red K. So we'll start with a kangaroo here. This means a beaver will be here, and a kangaroo must be here because kangaroos still have to have kangaroos next to each other. This square will be a beaver because this kangaroo already has the kangaroo, so we want a beaver here to max my beavers. We want another beaver here, or else this beaver will have two kangaroos next to each other. And we could see a pattern emerging where it's just repeated steps of the beaver, kangaroo, kangaroo, beaver sequence. So we just continue this pattern, eventually finding how many beavers are there at maximum. As you can see, in the end, there are 2, 4, 6, 8, 10, 11 beavers at maximum. So the answer is D, 11. Question 17. The number 5 to the power of 5 to the power of 6 can be written in the form of n to the power n for some integer n. What is the value of n? To do this, we start with the given 5 to the power of 5 to the power of 6. Then we use this exponent law to simplify, to change the exponent to 5 to the power 1 times 5 to the power 5. Then we evaluate 5 to the power 1 to become 5. Now we use this exponent law to bring the 5 to the base to get 5 to the power 5 to the power 5 to the power 5. This gives our answer of C, 5 to the power 5, since n is 5 to the power 5 in this case. On a rectangular prism, which net could show his path? We start by looking at making an empty net to show all the paths. For instance, if a path was going up here, I would like to denote where it would end up. So if we went up from here, we would end up all the way here, and vice versa. If we go up here, we would end up here. We'll repeat this for every edge. This side goes up to here. This bottom side goes here. This side goes here. Then this side goes here. Then this side goes here. Then side goes all the way here. And this side goes all the way here. And this side goes here. This shows all the paths. So now let's look at how we use this diagram to aid us. For instance, let's take A. If we go here, we must end up all the way here from our diagram. This goes all the way here. Then this one goes up here, and we have an issue. There is nothing here. So A cannot be correct. For B, we start here. This one takes us all the way here, and there's nothing here. So this is also wrong. For C, well, this up goes, well, we'll start here. This one goes all the way here, which is a dead end. So this one can't be correct. D will start here. This one goes all the way here, which goes here. This one goes here, which goes here, and this one goes here, which makes a complete loop. So D works. And of course, if we check E, because it's always a good idea to check all of the answer choices if you have time, we start here, we go here, and there's nothing here. So E can't be correct. So the correct answer is D. Question 19. A pentagon is divided into smaller parts as shown. The numbers inside the triangle indicate their areas. What is the area of P, the shaded quadrilateral? First, we will split up P, like shown, into two different parts. Then we'll evaluate the parts individually, starting with P1. Let's label some lines, like so. So that's 8 and that's K. You can use any variables you want. These are just some arbitrary variables. Now, we know that AH over 2 is equal to 3 because of this triangle here. We're assuming that H is the height of the triangle here. Then we know that BH over 2 equals 2 because from this triangle here. So now, using our two facts, we make this equation. We know this equation is true because if we substitute AH over 2 and BH over 2 here, we get 6 equals 6, which is a true fact. Now we divide both sides by h over 2, and then divide both sides by 2 to get A equals 3b over 2. Now we are going to use another triangle. We know that AK over 2 is equal to 9 because of this triangle here. So, we know that AK over 2 is equal to 9. So now we take our 3b over 2 and substitute it into our A to get this 3b over 2. Now we simplify to get 3bk over 4. We multiply 2 on both sides, and then we divide 3 on both sides. And now, very coincidentally, we get the area of this triangle, which is what we are trying to figure out at the start, P1. Now we have to repeat the same thing for P2. So I will label this one here. So N, M, C, D. We start with dm over 2 is equal to 4. So we know this from this triangle. Then we multiply 2 on both sides to get that dm equals 8. Now we have cm divided by 2 is equal to 8. We know this because of this triangle. So, and when we multiply 2 on both sides, we get cm equals 16. Now we know this statement is true since cm 2 times 8 equals 16 when we substitute these values. And then we divide m on both sides, and then we divide 2 on both sides to get that d equals c over 2. Now we have dn is equal to, divided by 2 equals 5. We get this from this triangle. Here. Then we have the fact that dn is equal to 10. This is what happens when we multiply 2 on both sides. After that, we substitute our c over 2 that we got here to d. And then when we do that, we get that cn over 2 is equal to 10. Coincidentally, this is what we were trying to figure out the entire time over here. 2. This gives us our final answer. So now we know that this side is 10, this side is 6, this one is 6. So we add them to get our final answer of 16. Question 20. How many integers are factors of 2 to the power 20 times 3 to the power 23, but are not factors of 2 to the power 10 times 3 to the power 20? To do this question, we take our useful trick that between a and b, there are b minus a plus 1 numbers, including a and b. The factors of 2 to the power 20 times 3 to the power 23 must be of the form 2 to the power a times 3 to the power b, where a is between 0 and 20 and b is between 0 and 23. Note that we got these numbers from the prime factorization, like so. This means since there's 21 numbers between 0 and 20, and there are 24 numbers between 0 and 23, there are 504 factors of 2 to the power 20 times 3 to the power 23. Now we repeat the same thing for 2 to the power 10 times 3 to the power 20. We have a being between 0 and 10 and b being between 0 and 20. So hence there are 11 times 21, or 231 ways. Notice that all the numbers that are a factor of 2 to the power 10 times 3 to the power 20 are also factors of 2 to the power 20 times 3 to the power 23. This means that we can simply subtract these to get our answer of 273, or C. Question 21. Two functions f and g are on R's so that they satisfy the system of equations f of x plus 2g of 1 minus x equals x squared and f of 1 minus x minus g of x equals x squared. What is f? To do this question, we start by substituting x for 1 minus x. When we do this, we start with our f of x plus 2g of 1 minus x equals x squared, and we substitute our 1 minus x into the x terms, all x terms specifically. When we do this, we get this messy equation, which can be simplified into this. Now, why did we do that? Because now, if you notice, the f of x turned into f of 1 minus x, and the g of x turned into the g of 1 minus x turned into g of x. This is important because these terms are very coincidentally the same ones used in our other equation, as shown here. These ones are just the same terms in our other equation. So then we can substitute a equals f of 1 minus x and b equals g of x. In reality, there won't really be a change when you substitute these, but it does make it easier because you don't have to write this term or this term like 10 times in a row. It makes it much easier. When we substitute this, we get this, which is a very nice and pretty simple system of equations that we can then solve. We subtract the two equations. So basically, we have a plus 2b, and we have a minus b, and we subtract these two equations to get 3b. And that's basically what we've done here. So when we subtract these two, we get 1 minus 2x is equal to 3b, which then very quickly simplifies it to b equals 1/3 minus 2/3 x. Now, if we look at our definitions, we know that b isn't the answer. B is just g of x. We need f of x. So now, obviously, we substitute into the second equation, which is this equation. Why second equation? Because it's simpler. That's actually the only reason. If you did it on the first equation, it will give you the same thing. So we substitute, we distribute the negative side, and then we move everything to one side, and we found A. Unfortunately, it's still not the correct answer. A is f of 1 minus x, not f of x. The question was originally asking f of x, f, not f of 1 minus x. So, continuing our spree, we go and now we substitute a to f of 1 minus x. Because now we're done with this basic notation. Now we are going to substitute x to 1 minus x again, just like we did with at the start to convert x into 1 minus x and 1 minus x to x. Now we're going to convert 1 minus x to x. So we substitute that, and we get this absolutely ugly equation that we simplify, obviously, or else this wouldn't be an answer. So we distribute a lot of things and then combine like terms to get f of x equals this, which is the answer. After that, we rearrange the terms to get to end up getting one of the answer choices, which is our answer of A. Question 22. In a bouldering competition, 13 climbers compete in 3 categories. The score of each competitor is the product of their rankings in the 3 categories. For example, if one is 4th, 3rd, and 6th, their final score is 4 times 3 times 6, or 72. The higher you score, the lower your overall ranking. Hannah ranks first in 2 categories. What is her lowest possible overall ranking? We start by noting that Hannah's highest score that's possible is 13. This is so that everyone else, this is not the answer clearly, but it tells us that everyone who beats Hannah must score below 13. So obviously, we would have some place to put all of the competitions and scores. So here every single column includes one competition and each row includes one place number. For example, Hannah got first place, and 13th place, which I didn't include, which I'll represent in red. Now we need to find the maximum number of other people who could have gotten a score lower than 13 when you multiply them. If we were to maximize the score, basically make sure everyone gets 12, ideally we would have 2 possibilities. Well, not really 2 possibilities, 2 players. The person who gets 1 first place, 3rd place, and 4th place. And the person who gets 3rd place, 2nd place, and 2nd place. A 3rd person is not possible because if we take the lowest of all of them, 2, 3, and 4, 2 times 3 times 4 is clearly greater than 12. It's 24. So clearly, we cannot improve this. So there is only 2 people going to be better than Hannah. Since no matter how hard you try, you won't get any worse score for Hannah. No matter how hard you try, only 2 people will beat Hannah. So since there's 2 people beating Hannah, the answer is 3, which gives our answer as B, 3. Question 23. A spiral of consecutive integers numbers is created as shown starting with 1. When the pattern of the spiral is continued, in which arrangement will the numbers 625, 626, and 627 appear? The first thing I notice is the number 625. Why, you may ask? Because 25 squared is coincidentally 625. I wonder why they decided to make it a perfect square. That's not normal usually for large numbers. So for now, we're gonna extend this pattern like this, and then we're gonna look for some patterns with perfect squares, because 25 squares just happen to be. We notice a very distinct pattern if we just simply box in all the perfect squares. They form this beautiful diagonal with odd perfect squares being shown in red and even perfect squares being shown in blue. How subtle of an effect this is that it forms a diagonal. And also very coincidentally, every single number is 1 away from a turn. 625 is one of the odd perfect squares. So it will go up and then turn right, which means it will be B as our answer since it goes up and then turns right. It wouldn't be D because that goes right and then turns down, which is not here. So our answer is B. Question 24. A block in the shape of a regular tetrahedron has one face shaded. The shaded face of the block is then placed on the board on the triangle labeled start. The block is then rolled from one triangle to the next by rotating it about one edge. On which triangle will the block stand for the first time again on its shaded face? We will now proceed by labeling all the vertices. So I'll let this one be A, this one be B, this one be C, and this one be D. And then I will label this start square with this bottom face. This bottom face will represent our start square, where we'll start on. And then whichever triangle is the answer, we will also have ABC, which means that same face. ABC is showing the face that is on this triangle. This B is representing that the vertex B is on this point. That's what basically all these numbers actually mean. Now we're gonna rotate it across line BC. Now this, for your convenience, is line BC. If we rotate our triangle ABC out around line BC, we get D. So D will be our center. Now we repeat this process. Now we're going to reflect it across BD. BD being this line. If we take triangle BCD, which I'll just show you, which is this triangle over here, we get that our answer is A. If you were smart, you would notice that for every reflection is the one point that we have not mentioned in the triangle that we're reflecting. So basically, for example, the next one, which we have AD, we have triangle BDA across AD. The one point not in BDA is C, and that would go here. If you were smart, you would understand this basic pattern and go forward. So now we will do another reflection across CD, which is this line. So whichever method you choose, you will get B. And now we have DB again. So I'll just use the same color. Here we got DB again. So we'll use that and get the A here. We still have no ABC triangle anywhere. This is ABD, this is ACD, this is DCB. But on our last reflection around AB, we get C here, and hence we have made a triangle ABC again. So hence, since on triangle E we got our bottom face to become ABC, the answer is E. Question number 25. Part of a fifth-degree polynomial shown cannot be seen because of an ink blot. It is known that all 5 roots of the polynomial are integers. What is the highest power of x minus 1 that divides the polynomial? We are going to use something called Vieta's formulas, which can easily tell us the product and sum of the roots using a few formulas. In this case, the sum of the roots is 11, and the product of the roots is 7 by Vieta's formulas. Now we just gotta use 2 equations. These two equations come from Vieta's formulas, where A, B, C, D, and E are the roots of the polynomial. Now, why are we worried about the roots of the polynomial? Because the highest power of x minus 1 is just how many roots are 1. So now we're gonna have to set one of these and, well, do math. The only solution that works for this is letting A equal 1 and then having everything else being 1. B, C, D, and E are all going to be 1. This is the only solution that works, and it gives us 2 true statements. 7 plus 1 plus 1 plus 1 plus 1 equals 11, and 7 times 1 times 1 times 1 times 1 equals 7. Since there are 4 roots that are 1, the answer is D, x minus 1 to the 4th power. Question 26. The large square is divided into 4 smaller squares. The circle touches the right-hand side at its midpoint. What is the side length of the large square? In order to do this question, we're going to make a variable that this side is x. Now by logic, this entire side is 8 plus x, which means this entire side is 8 plus x, which means by logic, since this is the midpoint, this side is also 8 plus x. Now how on earth do we find the radius from this in terms of x? Because that's what we're going to try to do, find the radius in terms of x. So now we know that the diameter, which is just 2 times the radius, is equal to 8 plus x, which is 8 plus 2x. Then we divide 2 on both sides to get that the radius is 4 plus x. Now we don't know x, so how does this help us? Well, simple. We're just gonna find another way to find the radius. We're just gonna find the radius again, even though we already know the radius in terms of x. What I mean. We're gonna let this side is still x. This side must be x plus 2, because then only x plus 2 plus 6 will equal x plus 8, since this is a square. Now, we're going to, again, we're gonna draw the center of the circle, and I'm gonna mark this as O. This length is the radius, 8 plus x, minus this length, which is the radius, which is 4 plus x, as we found earlier, is 4. And now, this length is, guess what? The radius also, because it's going from the center to one of the edges of the circle. So now we just can use, and now, since this is a square, we know this is a right angle, and we can use the Pythagorean theorem. So we get our two equations. This second equation came from the Pythagorean theorem, and the first equation came from basic math. Now we set them equal since they both are the radius of the circle, and solve for x. We start by squaring both sides. Then we expand the square terms, and then we simplify a bunch. We subtract 16 on both sides and then divide 4 on both sides, and we find that x equals 1. Note that 1 centimeter isn't our answer, since that's not what the question asked. The question asked the side length of the large square, not even the radius. So now time to scrap everything, since now we know x. Since this is 8 plus 1, this length is 9 centimeters. Since this length is 9 centimeters, this length is also 9 centimeters since it's the midpoint, and hence the side length of the large square is 18 centimeters. Hence our answer is 18 centimeters, or A. Question number 27. What is the greatest common divisor of all numbers of the form n cubed times n plus 1 whole cube times n plus 2 whole cube times n plus 3 whole cube times n plus 4 whole cube, where n is a non-zero natural number? To do this, we can find the greatest common divisor of n times n plus 1 times n plus 2 times n plus 3 times n plus 4, and then cube it. Let's take a set of 5 consecutive integers. One of them must be divisible by 5, since if we note down the possible remainders of the first term when divided by 5, we get this. Now, this probably makes no sense, but every single one of these sequences have a remainder of 0. The remainder of 0 tells us that that number is divisible by 5. If a number divisible by 5 is multiplied by any integer, it will always still be divisible by 5. Any number divisible by 5. So, by logic, since at least one of the integers, no matter what, is divisible by 5, the product must also be divisible by 5. Now, we're going to repeat the same thing for all the other numbers. Get ready. Now we're going to do for divisibility by 4, which we get this. Now we look at all the zeros. This one, well, that has 2 zeros. This one has only 1 0. This one only has 1 0. This one only has 1 0. Duh. Since there's at least one number with no remainder, no matter what, it will also be divisible by 4. Similarly, for divisibility by 3, again, we copy the same thing. There are 2 zeros in this one. There is 1 0 in this one. There are 2 zeros in this one. Since every single one of them has at least one zero, it will be divisible by 3 no matter what. Now divisibility by 2. This is the hard one. For divisibility by 2, there is a minor issue. Some of these could be divisibility by 4 also. And considering divisibility by 4 could also have 2 divisibility by 4 if we circle back, this isn't a guaranteed win. Luckily, if we match these to the divisibility by 4, note that if it has a remainder of 2 when dividing by 4, it must have its remainder 0 since this is even. If we look, no matter what, there's at least one extra divisibility by 0 that is just non-existent here. So, no matter what it is, it will always have at least one that is divisible by 2, but not 4. Now, since at least one number is divisible by 2, but not 4, 3, 4, and 5, it must be divisible by 2 times 3 times 4 times 5, or 2 cubed times 3 times 5. Cubing it gives our answer of 2 to the power 9 times 3 to the power 3 times 5 to the power 3, which is answer option number E as our answer. And we can already be sure that there is no other common factor because this is actually the largest number of all the other 4 possible answers, so we don't have to check any further. Question number 28. The numbers from 1 to 11 are to be placed in the hexagon so that the sum of the 3 numbers around each of the 6 black dots is the same. 3 of the numbers have already been placed. What is the number that will be placed in the hexagon with the question mark? We're going to assign a few variables here. We'll let this one be x, this one be y, and this one be z. 3 variables. Now we're going to continue, knowing that the sum around the 6 any of the 6 black dots is 6 plus x plus y. And that's because of this black dot, in case you were wondering. No, I'm not making that sum up. It is from this black dot that you know that the sum is 6 plus x plus y. So we continue. This one is 2 plus x, because 2 plus x plus y plus 4 is equal to 6 plus x plus y. This one is annoying. It gives you this one will give you minus z so that it cancels out with the z. We must add y, and then we must add the 6. So 6 minus z plus y. Now we're gonna look at this bottom one. So we need 4 more in the constant. We need a y and we don't want a z. So we have this 4 plus y minus z. Now we're going to do this one. So we have an 11 here, so we need a minus 9 to bring that down to a 6. Then our z, we need a z, and then we need an x. And now this last term coincidentally cancels out. We need a 6. No, wait, we need a 9. Then only we'll get a 6. And then we already have the x, we already have the y, and the z's already cancel out. So in the question art, the only number can go there, even if all the other numbers could be some convoluted mess. The only number that can be in the question mark is a 9. Question 29. Two identical cylindrical water tanks each contain the same amount of water. One important information. One cylinder is standing upright and the other is leaning against it, and the water level in each of them is the same as in the picture. That is another piece of important information. The bottom of each of the water tanks is a circle with area 3 pi meters per meter square. That's also a very important piece of information. Well, how much does each of the water tank contain? Of course, that's an important piece of information because you can't solve the question without it. Alright, so now we have underlined a lot of pieces of information. So let's go through each. The first one says that they contain the same amount of water. Well, to do that, we need to know the height of the cylinders, which we don't, so let's make a variable for it. Let the height of the cylinders be h. Well, the standing upright one. Well, then I'm just going to construct this right angle. And then I'm going to let this side be a for no specific reason. Now we're going to use this fact that they contain the same amount of water to get that 3 pi times h is equal to 3 pi times a over 2. The reason why we divide 2 is because if you split it like this, we notice that the water takes half of the entire cylinder since the cylinder is tilted. So that's why it's just divided by 2. If we solve this, we get that a equals 2h. So we are going to replace our h, a, with one less variable, progress. So now we know that this is 2h. Since this is a rectangle, this is also 2h. Now, what I notice, well, we know this is a right angle. This is a 30, 60, 90 degree triangle. Well, this is the 30-degree angle, and this is a 60-degree angle. That's the thing that we notice. But how on earth do we find the height? Well, we only used one of our pieces of information, so let's continue. The water level, we kind of used it already with the area. The bottom of each of the cylinder is a circle of 3 pi. That's the one information we haven't used, other than calculating that area. So let's do that. We have this formula. If we look at the circle at the bottom of the cylinder, we have pi r squared being the area of the circle equals 3 pi. This means that r equals root 3, which also means that this length, which is the diameter of the circle, is 2 root 3. So how on earth does this random number in the exact wrong place helps us? Well, if we draw this perpendicular here down, well, now we can see a nice pattern. Since this is a right angle, we know that this is by logic 60 degrees, which means by logic this is 30 degrees. Kaboom, another 30, 60, 90 degree triangle. So since this side is 2 root 3, we know that by that logic, this side will be 2, and this side will be, no wait, this side will be root 3, and this side will be, can you guess it? 3, because root 3 times root 3 equals 3, which means since these two are equal, h is equal to 3. Now using again our red fact, we know that the area is 3 pi, the volume of all the water in these containers is 3 pi times 3 pi the base times the height, 3. which gives us an answer of 9 pi, or alternatively C. Question number 30, the finale. The product of 6 consecutive integers is a 12-digit number of the form ABBCDDCDDABB, where the digits A, B, C, and D are themselves 4 consecutive numbers in some order. What is the value of the digit D? Alright, let's start with the most basic fact. We know that the product of 5 consecutive integers is divisible by 120. Look at question 27. I already explained why it's divisible by 120. This means that the product of 6 consecutive integers is divisible by 120. Fun fact, if you actually want to go through the pain of proving it, it is also divisible by 720. Look at question 27 if you want to see how you prove for 120, and you can probably understand how you do it for 720. This means that it is divisible by 10, since 10 is a factor of 120, which coincidentally means that it ends in 0. This makes B equals 0. The other 3 numbers are 1, 2, and 3, because those are the other 3 numbers that it could be divisible by. Since the product of 6 consecutive integers is divisible by 120, it must be divisible by 3. This means the sum of the digit in ABBCDDCDDABB must be divisible by 3. Now we get this mess. This equation, 2a plus 2c plus 4d, which is the sum of all the digits, must be divisible by 3. This is a divisibility rule, in case you were wondering. And if you don't know divisibility rules, I don't know what you're doing, you better go and learn them, because they're extremely useful. Even more useful than Vieta's formulas. This means that 2a plus 2c plus 4d is divisible by 3. Now we just have to guess d equal 1, d equal 2, and d equal 3. Notice that the other 3 numbers are the other 3 numbers for A, C, and D, since we know that they're consecutive. So now all we need to do is guess them. Note that A and C are interchangeable, and we get 3 options. The only one that works is D equals 3, because then this means that only D equals 3 works, which gives us our answer of C.
Don't forget to subscribe and like. If you have any questions, you can email info@agoramatterco.org or comment below and we'll reply back. Maybe. And if you want to see practice things or anything about us, you can visit our website, which is basically the end of the email but without the info and the end. So bye!